All right, so today we're starting a new unit. This is the last unit of the year, magnetism. So the first question I have for you is, up on the board I have a picture of a coil and a bar magnet. What's the difference between the two?
The coil doesn't have any electric...
Well, the coil is actually hooked up to a battery.
Oh, okay.
Via wires.
Nothing.
And current is... They are exactly the same thing! A coil of wire and a bar magnet are functionally identical. Did you guys know that?
Yep. Yep.
Did you do that last year?
Yep.
Yeah. Yes! All right, cool. So yeah, it's a crazy, crazy thing to think that they're the same thing, but they are. Now, if the current isn't flowing in the coil, is the coil a magnet?
No.
If there's no current in it.
No.
So there's something about the moving charges in the coil that makes the magnet, wouldn't you agree?
Yes. Yes.
Okay. So this leads us to the final topic, most important topic of the unit, which is, what is the source of all magnetism?
Moving charges.
Moving charges. All right.
We did this last year.
So, if magnets are just moving charges, and permanent magnets are magnets, that means permanent magnets must have moving charges, right?
Yes.
What are they called? If permanent magnets have moving charges in them, what are the moving charges in the permanent magnet?
There's a term for them?
Yes, there's a term for them. What are they called? Okay, so let me step back a little bit. Is a magnet made of atoms?
Yes.
Yes.
Ions. They're ions. Frisbee ions.
No. Actually, not ions. So that is very smart sounding. Yeah, they're not ion. Wait. Magnets are made of atoms, and what do atoms have in them? Electrons, right! Are the electrons in the atoms inside of the permanent magnet moving?
Yes.
Yes.
Or no? Yes, they
Yes.
must be.
But wouldn't they be moving
How?
the coil too?
Oh, I agree. But copper, if you have a big solid hunk of copper, is it magnetic? Yes or no? Do you guys know this? Big solid hunk of steel. Can a hunk of steel be magnetic?
No. Not alone.
Well, it could. Could.
But it doesn't have
Ever
to be
taken
like...
a pair of scissors and going, open and close, open and close, and open and close, and then you can pick up paper clips with it? You've never done that?
I need to do this now.
Can we
Oh,
do
it's very
that?
cool.
Can we
Again,
do
all my scissors are next door. Shoot. I'll have to get a pair of scissors and try it someday. Yeah, but yeah, you can actually magnetize a pair of scissors, and it's just made of steel, and you go over and over again, and you can pick up stuff. And that's pretty cool. Well, let's go back to this question. Are permanent magnets, we know they have electrons in them, but are the electrons moving?
Yes.
Yes, they are. How so?
They would be like generally in one direction.
Oh, they go shaky, 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 shaky. Well, the point you bring up is a valid point. Like, in order to be magnetic, don't they have to generally be moving in the same way somehow? Or otherwise, there's a magnetic field that was created, it would all conflict with itself. Like, every electron would be creating a different one, and you'd have no net magnetic field, right? Right. So, the question is, how do you get a magnetic field just from an electron? How is the electron? Raise your hand if you took chemistry. Raise your hand if in chemistry you talked about something called the Pauli exclusion principle, which had to do with SPDF orbitals and electron filling and all that mumbo jumbo. You remember that?
Yeah.
Remember what the rule was? You draw for every up arrow, you try to end up drawing a down arrow. Yeah, and you end up with a bunch of up arrows and down arrows. And whoever your teacher was said something to the effect of, "Oh yeah," and then this electron is an up electron, a spin up electron, and this electron was a spin down electron, what am I doing with my hand right now? Right hand rule. A spin up electron is spinning this way. A spin down electron is pointing your thumb down, is spinning the other way. Now it turns out if you have a solitary electron that's spin up, it's going to create a magnetic field around itself. In one direction, spin down, it's going to create in the other direction.
When you say spin down, you just mean like it's spinning it one way, but it's
Yeah,
not
yeah,
actually
yeah.
going down.
Correct. It's not moving down, it's just down is our way of indicating spinning in this direction, versus up is spinning in the other direction, clockwise versus counterclockwise.
Since they could use clockwise would then be easier.
Yeah, but that's 3 letters rather than a single arrow. Right? Or if you want to draw a clockwise arrow, you draw it like this versus this. And that's more difficult typographically than just doing up or down. Good? Alright, so yeah. So if you take an element like iron, you see where it is on the periodic table, number 26, right? It's right in the middle. Turns out iron, I think, typically has maybe 2 to 4 electrons that are unpaired, and that's what makes iron make a real nice magnet. Well, maybe not a real nice magnet, but a halfway decent magnet. All right. So anyway, source of all magnetism is moving charges. So, do you guys, who here has ever used a compass before? Raise your hand. Okay, everybody. That's awesome. What's a compass for?
It's to tell directions based on.
So what's it do?
It points to north.
South. It's the magnetic south.
I haven't
It
heard the
points
right answer
towards
yet.
the North Pole.
Wrong. It doesn't
The
point toward the North
needle
Pole.
gets pulled towards the North Pole from
Ah,
the magnetic
no.
field.
Ooh, I like that answer. Magnetic field. Compasses are magnetic beasts, right? You know this. And if you want proof that a compass doesn't point north, all you have to do is put the compass on the table, grab yourself a handy dandy hard drive or some other permanent magnet, and go like this and feel the world spin. Right? Because if the compass was pointing north and north was changing like crazy, that would mean the world was going like that every time you drag the magnet around. Clearly,
So
that's
it
not
points in the
happening.
direction of the strongest magnet.
It doesn't point in the direction of the strongest magnet. What it does is it aligns itself with whatever the magnetic field is that it's currently in. A compass aligns itself. So what I mean by that is this. Let's say you had a magnetic field that was pointing to the right and the compass wasn't. What will the compass needle do?
Turn.
It'll go boing, and it'll have a torque boing, that'll cause it to align left-right. Yes.
So how come it won't go the other way? How come it only turns this way instead of turning the
Long
opposite
way,
way?
the
Yeah.
long way around.
Yeah.
Oh, it'll turn the long way around.
Oh.
Yeah, because the magnetic field has a direction, right? And the compass has the ability to align itself with whatever that direction is. If it's north and the compass needle is aligning itself such that it would be wanting to point south, the compass needle will go wing and rotate through 180 degrees to get where it would need to go. Make sense? All right. So, but also what that means, which is very interesting, is say we took a look at the board and we put a compass right here. Which way would the needle point? Would it be point toward the North Pole or toward the South Pole? Would it point this way or would it point that way? Neither. It would point straight up and down. Why? Because the line is straight up and down at this point, right? Does that make sense? So when people say, oh, it points north, no, it doesn't. It aligns itself with whatever the magnetic field is where it's sitting. All right, which is going to depend on the fact that you have a north up here and a south down here, but the compass doesn't know that. All the compass knows is what it's sitting in. But what this also means about compasses is they're really handy as a magnetic field detector. All right? If you have a magnetic field, you can find it with a compass. Or at least you can sense a change in magnetic field as you move the compass around. All right? And this leads us to the really cool demo that I can't do because it's next door. So I will simulate doing the demo.
Is this going to be as cool as the actual demo?
No. Almost, but not quite.
We should walk next door.
All right.
Can't we
That's
just walk
over
next
in,
Field trip,
in the other
field trip.
hallway. Anyway,
Let's go.
so what we have here is a wire that's oriented vertically. And there was a guy by the name of Carl Oersted. I don't know, he's dead now. Maybe 160 years ago. He was playing around with batteries and wires and stuff. And he set up a wire like this. It was vertical. Then the top end of the wire he connected to the top side of the battery. Bottom end of the wire he connected to the low side of the battery so he could get current flowing in the wire, right? So let's pretend like there's current flowing in this metal bar and the current is flowing upward. So what Oersted had was he was playing around with a magnet too, and he noticed as he got close to the wire, the magnet or the compass, what did it do? It went boing, 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 boing. He's like, whoa, that's interesting. And then as he got closer to the wire, the effect got stronger. What's that mean?
It's a discovery.
The field is stronger closer to the wire.
Yeah, he knew that a compass works on magnetism, on magnetic field, and he also therefore correlated the fact that there was a current in a wire creating a magnetic field. So he's kind of the first person to figure this out. All right? And moreover, what did he find when he got close to the wires? Depending on where next to the wire he put the compass would point in different directions. Like, for example, if he put the compass in front of the wire, which way did the compass point? Kind of left, right. If you put it on the right side of the wire, the compass would align forward, back. If he put it behind the wire, the compass would align left, right, and so on. And so what he realized is this wire was creating this swirling magnetic field around itself. And then he also realized that when he disconnected the wire and the current went away, what happened to the magnetic field? So he realized that a current-carrying wire is its own magnetic field creator. Does that make sense? And so that's the link between electricity and magnetism. Current in a wire makes magnetic field. And moreover, he realized that if the field was swirling around, he had this idea to stick his thumb along here and then curl the field around, and you have the right hand rule.
He came up with that?
I don't know if he came up. I just made that one up, but somebody did. And that's the right hand rule, right? And so it comes straight out of Oersted's experiment. Sound good? All right. So, and then, of course, like we said before, he figured out that the farther away you get, the weaker it is. The closer you are, the stronger it is. Now, here's a question. I have a wire. It creates a magnetic field. Fine. And how does the strength of the magnetic field depend on distance? Is it 1 over r squared? Is it 1 over r? Is it nothing? What's the relationship? What should it be? And you guys should be able to logically figure it out. What should it be? Hint, it's a wire.
It's on
What's the relationship?
It's 1 over r.
Why should it be 1 over r? It's just like the E field argument, which was,
They only change in one direction.
yeah, it's only gonna, the field is only gonna get spread in one direction, right? So, yeah, so the field from a wire should drop away according to 1 over r, not 1 over r squared. All right. Okay. Now we're also going to pretend like we had a bunch of wire in our hand. Imagine if you will, that I was holding wires in my hand like this. You're going to have to imagine really hard to visualize this. All right, and I take this wire and I create a loop out of it.
I
Like
actually
that.
have wires in a loop. You want those?
You have wires in a loop?
Headphones, but they loop really well. Better than what that looks like.
Oh, come on. Work with me here. All right, so I got wires in a loop. Woo! And let's say I had current flowing, let's see, from your point of view, clockwise through the wire. All right? Now, what I want everybody to do is pull out your trusty right hand. Pull out your right hand, not your left one.
No.
Wait. Yeah,
All right, and
right?
we're saying that the current's going to flow this way in the wire. What I want you to do is tell me what is the direction of the magnetic field that's going through the middle of the wire. Which direction is it?
That towards you.
It would be, no matter where I lay my hand, when my fingers are inside the wire, they're pointing toward the front of the room. So as long as the current is flowing this way, the magnetic field is shooting toward the front of the room through the wire.
Oh. I thought you curl your fingers to be where you want.
No,
I
no, no,
see,
no.
I see.
Thumb goes in the direction of the current flow. These are your field fingers. Right?
Yeah, forget spirit fingers.
Field fingers. But it's only for right hand. Alright? Good? What are you drawing? That's too many fingers. You're like 9 fingers on one hand. 8? Okay.
Why?
I don't know.
The alien physicist words.
All right, so you guys got how to do this. So on your homework, you're gonna have to do this. All right. So let's say you have a bunch of wire loops, and let's see if we can figure out what the field direction should be. So I'm gonna go up to the board and look at this. So I'm gonna take my thumb, and the thumb is gonna go along the front edge, right? It goes up along the front, down along the back, right? Everybody do this with me. Up along the front, down along the back. So you feel field curls into this coil. That means it's going to shoot this way through the coil. Does that make sense? All right. So, and we say that the end of the coil where the magnetic field comes out of is called the north end, and the end of the coil where it goes into is called the south end. Good? And then right beneath that, I put a permanent magnet. Hey, look! What do you notice about the magnetic field? It's exactly the same. Huh? Coincidence? I think not. All right. So, here's a question. You know how I labeled this this permanent magnet with the north side and the south side? What would happen? What would happen if you sliced that permanent magnet in half? Would you have a north piece and a south piece?
No.
Why not?
Just south.
The magnet would just break into 2 smaller magnets with their own.
Think of it as a coil. Like the coil above it. Yes. The coil above it. If you split that coil in half, would all of a sudden you only have a north side of the coil?
No.
No, that makes no sense. So permanent magnets are just the same as coils, right? You don't end up with just a part where the field comes out, because where's it going to go? Got to go back in, right? So yeah. So that's the explanation. You can't have what's called a magnetic monopole, at least not in classical physics. But you can't have a magnetic monopole where you just have a north end of a magnet and just have a south end of a magnet, because magnetic field is unlike electric field. Magnetic field loops around and comes back
So
to
you're
where it came
saying
from.
you can have a magnetic monopole in other branches of physics?
There is, a few years ago, somebody claims to have isolated a magnetic monopole. I'll leave it at that. All right, yes. With a different understanding of what magnetic field is than I'm willing to go in this class. All right. Again, this is a classical physics
Does that
class.
mean that it's too advanced for us, or he was wrong when he did it?
It means I have no idea. I am not qualified, nor do I have the level of understanding to explain it to you.
So if
You
it
get
was a
someone with a
monopole, would it
PhD.
either all just point in or all just point out?
Yeah, right. That would be what my understanding of it would be, which wouldn't make any sense to me physically. Because again, I'm thinking as a classical physicist.
It's broken physics.
Right. So, anyway, so let's move on. As I punt your question, that was a great question. All right, so let's see. Keep on moving. Oh, this is interesting. So you know how we decided that a wire that has current in it will create a magnetic field, right? What if I was holding in my hand, say, a negative charge? Can you imagine that? I was holding in my hand a negative charge. Now, would this negative charge be creating an electric field around itself? Yes. Which way would it point? Toward the ball, right? Okay. So fine. Is it creating a magnetic field around itself? No, it's not. But check this out, Kohei. Watch this.
So throw it.
Magnetism.
When that negative charge was flying through the air, guess what it created?
Magnetic field.
A magnetic field that swirled around itself. But only when it was moving. Isn't that weird? Charges do create magnetic fields, but only if they are moving. And the second they are no longer moving, the magnetic field is gone. Got it? Okay. I just threw a negative charge. And as it was moving by Nirmal's head, it was creating a field at the location of Nirmal's head, right? What direction does the field point? Wait, it's a negative, right?
So it goes this way.
So left hand rule.
Or that.
Left hand is pointing in the direction that it's moving, which is creating a field that's wrapping around like this, right? So at Nirmal's head, which way is, so the field was pointing up. You guys got how that works? And then by the time it gets over here, the field gets weaker and weaker and weaker till the point where you don't even notice it anymore. Good? So the field is always strongest near where the charge is. So this is something called the Biot-Savart Law that we're going to talk about tomorrow. How many people are going to be out tomorrow? Nobody. Awesome. No prom fashion show attendees. All right. Good. Yeah, tomorrow is going to be a big day. We're going to learn about the Biot-Savart Law, which is basically the magnetic equivalent to Coulomb's law. All right, and we're going to redo all those problems. Remember how we started with a point charge and then multiple point charge, and then we did a straight line, and then we did curved lines and arcs? All of those exact same problems for magnetic field using the Biot-Savart law rather than electric field using Coulomb's law. So that's tomorrow. And we're going to go through all those integrations again. Sound good? Except now they're going to be even harder.
Oh, thank
Yes.
you.
All right, so here we go. Here is the picture of a proton moving through space. As it travels along, it creates a magnetic field. And then there's a neat thing on MIT OpenCourseWare, and the link is no longer there, so I need to update my notes. So I'll probably find that on a computer at some point and show it to you. But yeah, what I want you to do now is take a look at your packets, page 2 and 3, and get those done.